And I think the people that voted for Chapter 12 tests before we go on to 13 and 14 were wise to do that, because looking at it, you're going to be taking the derivative in Chapter 12 and learning what to do with the results. And in Chapter 14, you're going to be doing the same thing. You need to be able to take the derivative and then do something else with it as an application. So it's probably better to make sure you know how to take derivatives before we go on to 13 and 14. So we will do 13 and 14 as a combination. And I will look at 13 and 14 and see what I can do to streamline those two. We may not hit every single topic, because I want to have plenty of time to, yeah, I know it's just disappointing as heck, but we're going to run out of time. So I want to have plenty of time to spend on Chapter 15, which is integration. And it's kind of like shifting gears and going backwards. So Chapter 13 is about graphing and the derivative. In 13.1, we're going to look at increasing and decreasing functions. So before we look any further at that, tell me in common sense everyday English, what does increasing mean? 2 words. Going up.
I wanted to say it.
Yeah. No, don't hit me. Don't overthink things in calculus. Increasing means going up, and decreasing means going down. As long as you've got that firmly in mind, this section will not be difficult, okay? You have in front of you pictures of some functions. Assuming that the entire behavior of graph A shows everything that f of x ever does, what could you say about the behavior of the function x? Is it increasing or decreasing? It is increasing. It is not increasing at a constant rate, but it is increasing. It is constantly increasing, but not increasing at a constant rate. There's a distinction between those two. Okay? What about graph B? It is also increasing, but it is increasing at a constant rate because its slope remains the same through the entire domain of the function. This one, the slope changes through the entire domain, but the slope is always positive because the function is always increasing. Okay? What can you say about function C? It's constantly increasing. It never decreases, it always increases. And here again, it is not increasing at a constant rate. Its rate of change actually is constantly decreasing because it's growing at a slower and slower and slower rate. Okay, but its slope will never be negative, so it will not decrease. What about graphs D, E, and F? Let's talk about them all at the same time. What do you say about them? They're all decreasing. In fact, this is decreasing just like this was increasing at a constantly decreasing rate. This is decreasing at a constant rate. Its rate of change remains the same. This is constantly decreasing, but it decreases more and more as you go further and further. Don't overthink what this says. This is simply the math language for what you just told me. If you have a function defined on subinterval, any interval, then for any two numbers in that interval, x1 and x2, the function is increasing on the interval from x1 to x2 if the y value, which is what f of x1 says, if the y1 value is less than the y2 value, when the first x value is less than the second x value. Okay? That's just math language for what you just told me about graphs A, B, and C. And the same thing with the second line. If f is decreasing on the interval, if y1 is larger than y2, when x1 is still less than x2 or to the left of x2. So we're going to look now at an example. want you to examine this function for yourself for a minute. Make your notes. And tell me, where is this function increasing? Where is it decreasing? And where is it constant? Constant means it's neither increasing nor decreasing. And we're talking about intervals here. So if you look carefully, you're talking about the interval where x is less than 4, or x is from 4 to 0, when x is from 0 to 4, when x is from 4 to 6, and when x is larger than 6. So for each of those intervals, write down what you think the function is doing, and then let's see if we're all right. Where is f of x increasing? On what intervals? And there's two places where it's increasing. So give me where it begins and where it ends. It's increasing behavior. Josh, what do you think?
Negative infinity to -4.
Okay.
And then 4 to 6.
And it is increasing here, as Josh said, and it is increasing here. Because as you go from negative infinity to 4, it's constantly going up. And as you go from 4 to 6, it's constantly going up. Now notice that I didn't include the 4 in that interval. If you go back and remember your closed brackets and your open parentheses, I'm saying that when it gets to -4, it has a different connotation. Okay? -4 is not in that interval, because at the point -4, whatever that y value is, it actually does something different. It is neither increasing nor decreasing, because it stops increasing and starts to decrease at the value -4. Okay? So you might want to make a note of that. And the same thing at the value 6. At -6, it is neither increasing nor decreasing. Is the function ever constant? Is it ever constant?
Yes.
Where is it constant? From 0 to 4. It's constant, meaning its slope is, what's the slope of the part of the function that's from 0 to 4? What's the slope of every part of that segment? It's not positive because it's not increasing. It's not negative because it's not decreasing. So what's the only thing that's left? 0. So on the interval from 0 to 4, the slope is equal to 0. It is neither increasing nor decreasing. It is constant. And that's actually what's happening just for an instant at x equals -4 and x equals +6. But we don't say that it's constant at x equals 6 or that it's constant at x equals -4, because you can only talk about increasing and decreasing and constant over an interval, not at a single point. It has to be discussion of an interval. So where is this function decreasing? We don't have any choices left here. Where is it decreasing? -4 to 0? Yeah. From here to here, it is decreasing because it's constantly going down until it gets to 0, and then it becomes constant for a little while. And then where else? Somebody else.
6 to 10.
From 6 to 10? Or actually past 10, because we have an arrow here, we're really going on to positive infinity.
Yeah.
So from 6 to positive infinity, we know it's decreasing because once it gets to 6, it stops going uphill and starts going downhill. Okay? So what that means is that the derivative of this function is positive on this interval, then negative on this interval, then 0 on this interval, then positive on this interval, and then negative on this interval. Okay? Because if it's increasing, its slope is positive, therefore its derivative is positive. If it's decreasing, its slope is negative, therefore its derivative is negative. And if it's constant, it's not increasing, not decreasing, so its derivative is 0 because it's a horizontal line.
So negative slope equals negative derivative.
Exactly, exactly. That's what I want you to associate. Decreasing f of x is the same as f prime of x is less than 0 or negative. Whereas increasing f of x is indicating to you that f prime of x is greater than 0 or positive. And then of course constant means the derivative is going to be 0. So for practice, tell me when the function is increasing and when is it decreasing. Travis, where's the function decreasing?
It's on the.
The one that I'm looking at now, the one that says practice one.
Say where it's decreasing.
Where is it decreasing? Not on a point, on an interval. Which interval, before -1 or after? Before. So that interval is from -infinity, and it stops at -1. So it's decreasing here. Okay? Question, is it increasing anywhere or decreasing anywhere else?
It seems briefly from 2 to 4.
This 2 seems to correspond to the top of that. And it does change behavior at 4, so it's also decreasing from 2 to 4. Shannon, give me an interval where it's increasing. Just one. Okay, from -1 to 2, it is constantly increasing. And then where else? Somebody else. From 4 to infinity, it starts going up again. So tell me, on which of these intervals is the derivative positive and which is it negative? Okay, when it's decreasing, f prime of x is negative. Which means that when it's increasing, the derivative is positive. Chapter 13 mostly should be easier than chapter 11 or 12 was, because it's more visual, and I think that makes it easier to understand, which I think also has an inborn hazard because it makes you think that can't be right, that's too easy. Okay, but here's the deal. A function is like a roller coaster. It goes uphill, it levels off for a second, and it goes downhill, and then it goes uphill, and it levels off for a second, and then it goes downhill really fast. Okay? So the roller coaster analogy, I think, is a good one. Think about when the roller coaster cars are going up and when they're going down. Now at the top of your next page, we're going to talk about a test, and that's why I keep bringing up the derivative. I'm going to talk about testing for when the function is increasing and decreasing. So if f prime of x is greater than 0 or positive on an interval, that means that the function is increasing on that interval or going up. And if f prime of x is negative for every x in an interval, then f is actually decreasing in that interval or going down. And if f prime of x is equal 0 for all of the x values on some interval, then f is constant on that interval. In other words, it's horizontal. And note that the third condition is only correctly used to refer to an interval. We can't say that f prime of x at a point means it's constant at that point, because at any point, the function is neither increasing, decreasing, nor constant. It's just simply a value. Increasing and decreasing refers to slope. Okay, and you can't figure out slope from one single point although you can figure out a rate of change using calculus for that point. Another definition that is important here, though, is called the critical numbers. Critical numbers for a function are the numbers in the domain of f, where f prime of x is either equal to c or f prime of c doesn't exist. So at points where your derivative is either equal to 0 or the derivative doesn't exist, you have what are called critical points. Now I'm going to go back one page for just a second to kind of elaborate on the critical points. We're going to go back to our previous drawing and talk about critical points in those for a second. So remember, critical points are where either the derivative is equal to 0 or it doesn't exist. Okay? So the critical points for this function, that would help if I went back to the screen, wouldn't it? Okay. Critical points for this function are at x equals -4, because it is neither increasing nor decreasing at that point. Likewise for x equals 6. It is neither increasing nor decreasing at that point. But there's also two places on this function where the derivative does not exist. Can you tell me where those 2 points are? The derivative probably does exist, and in fact, from negative infinity to -4, it's always going to be positive. And the derivative still exists past here, because these arrows really are indicating that it continues that behavior on to infinity. So it's going down or coming up from negative infinity. But there's another criteria for where a derivative doesn't exist. It has to be where a derivative is where you can draw one single unique tangent line. So you can't have one single unique tangent line at a sharp point. Okay, somebody said 0. It's not a real sharp point, but you can't really draw a unique tangent line, because what it does is it stops at 0 for an instant and stays at that single value for an interval of values. So it sharply changes behavior here. So x equals 0 is a point that is a critical point. And that's because f prime of 0 on that graph does not exist. Is there another point where that happens? At 4. And there again, you have no single unique tangent, because that's almost a sharp corner. So at this point, at x equals 4, f prime of 4 does not exist. So it's a critical point. Okay? So your critical points are where either the derivative is equal to 0 or where it doesn't exist. And we're not going to talk about an interval as being a critical point, because it's a collection of points. So critical points are single points, single x values. So when we're looking at the second graph, practice 1's graph, we have a critical point here and here at x equals -1 and x equals 4, because the derivative doesn't exist. But we also have a critical point here at x equals 2, because the derivative is equal to 0. Okay? And I think it's easier to understand when it talks about critical points if you actually look at a graph and determine where the critical points are, because you can see where either the derivative is 0 or where it doesn't exist. So those are our critical numbers or critical points. And then the last thing talks about applying a test. It says locate the critical numbers for a function on a number line, as well as any points where f is undefined. Those points will make open intervals, which they will. And then choose a value of x in each of those intervals and decide whether the derivative is positive or negative in that particular interval, and use the test to decide if f is increasing or decreasing on the interval. So we're going to apply that problem with an example. We're going to see what we can do with this. So if you look at that example, and I'm going to need to get a sheet of paper here because I don't have that one printed out for you. I have the intervals printed out, but not the graph itself, or not the function. We're going to get the calculator and we're going to graph this interval, or actually we're going to enter the function, and we're not necessarily going to graph it to start with, because we want to find out all the places where the tangent line is horizontal, which means we need to find the critical values of this function. We're going to do x to the third plus 3x squared minus 9x plus 4. And looking back at the test says locate the critical numbers as well as any points where the function itself is undefined. And remember, the critical numbers are going to be where either the derivative is 0 or it doesn't exist. So what we want is not just the graph of the function itself, but we want to know something about the values of the derivative of that function. So I'm going to actually go to math and do the numerical derivative of the function that's in y1, and I don't want to retype y1. I'm going to be lazy and go to vars, y-vars, function y1 with respect to x for all values of x, and with that screen right there, and I'm going to write that screen down over here so you'll have it in a few minutes. So here's what we're going to do. Once you've got that in your calculator, we're going to hit second graph because we want to go to the table. Now, I'm not really interested in the y1 values, okay? And since I'm not interested in them, if you don't want to even look at them, you can come back here to y1, put your cursor on your equal sign and press enter. And when you look at your table, you won't even see the values of the function. You'll see only the values of the derivative, okay? What we want to look at is, we're not really looking at the x values. We don't really care about the x values. We're looking to see where is the derivative headed. And we see that as x goes from 6 on up, the derivative looks to me like it's positive and increasing. Do you agree with me? As I scroll down and let x get bigger and bigger and bigger, Y values are also increasingly positive. And I don't see that changing as I scroll further and further and further. So what I'm learning from the table so Y2 is getting larger and larger and larger, and it's positive. So that tells me what's happening is that the function itself is increasing, increasing, and decreasing, and it's increasing at a faster and faster rate. Okay? So let's scroll backwards a little bit. And to do that, I'll have to go back over to my X's. And notice what happens between 1 and 2. At 2 it is 15, the derivative is positive. What happens as I go from 2 down to 1? Is it still positive? Let's see what that Y value really is over there. It says it's 1e negative 6. Oh wait, not 6.1, sorry. What's 0.000001 close to? 0. Does the value at x equals 0 seem to indicate that that must have been the truth? Because what happened as I went from 2 to 0? I went from positive to negative, increasing, decreasing. There is a derivative, f prime of x is equal to 0. Probably at x equals 1. And then I notice as I go further down, yeah, I know we're coming close on time, so we may have to finish this up later. I'm still negative, negative, but then I go positive again between -2 and -3. Change signs again. And then it appears to be positive when it's less than -3. So we're going to pick up with that. We're going to look at that in more detail and try to make this sign chart that we see on this page. Okay? We'll continue 13. I will try to have some kind of a practice test cobbled together for you by the next time I see you.